In this video, we're going to talk about the idea of negation of sentences and statements. So a negation is just a sentence or statement where you just have the opposite truth value. So for statements, it's pretty easy. Here's an example of one. I love cheese. In fact, that is true, for me anyway. Everybody else has different opinions or may have a different opinion, so maybe this is false for you. But I love cheese, so that is a true statement for me. So the negation of that would be a statement with the same context that has the opposite truth value. So for me, the statement, I do not love cheese, well, that's false. So the negation of I love cheese is I do not love cheese. Now be careful here. It's very easy to say, well, if I love cheese is the original statement, well, the negation would be I hate cheese. But that's not quite true. It's a little more subtle than that. Imagine if this statement here, I love cheese, was false because I liked cheese, but I didn't love it. It's okay. Imagine I just found it okay, something I'd eat, but not something I loved. Then this statement, I love cheese, would be false. But I don't hate cheese either. So if this was I hate cheese, then that would be false too. So that wouldn't be a negation. So kind of the easiest way is just to say it's not whatever the verb is here. So I love cheese, the negation would be I do not love cheese. So that's how that works. For statements, it's quite easy and there's not too much to say. For open sentences, it's a little bit different because remember there's a variable in open sentences, and these become statements when you fill in that variable with an appropriate element in the domain. So let's look at an example here. So here we have the open sentence, province P ends in a vowel, or the name of province P ends in a vowel. And if you go through the 10 provinces of Canada, you find that that is true for British Columbia, Alberta, Manitoba, Ontario, and Nova Scotia, and it's false for Saskatchewan, Quebec, New Brunswick, Prince Edward Island, and Newfoundland and Labrador. All of these guys end in vowels. All of these guys don't. They end in consonants. So the negation of this is going to be the statement or the open sentence that has the opposite truth value. So province P does not end in a vowel. So the negation is true this time for Saskatchewan, Quebec, New Brunswick, Prince Edward Island, and Newfoundland and Labrador. So now the negation, which I'll do I guess in blue here, well, that is true for those 5 provinces, and the ones that do end in a vowel, the negation is false. So the statement province P does not end in a vowel is true for these guys and false for these guys. And you could reword this. If you're using the English language, there's lots of different ways of saying things so that the statements or open sentences would have the same truth values. So maybe I could reword it. Instead of saying does not end in a vowel, I could say ends in a consonant. And that makes sense because there's only 2 types of letters, vowels and consonants. So if I say it doesn't end in a vowel, then it must end in a consonant. There's no other choice. So I could reword the negation by saying province P ends in a consonant. And note there's lots of different ways of wording these things that are logically equivalent. So here's a second example. This is a little more mathematical. So let's say we have the statement or this open sentence B, and it's x is greater than 4. So x, and x is an integer. So I'm saying the domain, the things you can plug in for a variable x, you can plug in integers. So pause the video now and see if you can work out, first of all, for what values of x statement B, open sentence B, is true for and which values it's false for. And then see if you can write the negation of B. So pause the video now and try that. Alright, so let's talk about the truth values for B first. So B is true when X is, well, 4 is not greater than 4. 4 equals 4, so that's not true. But any integer bigger than that, so 5, 6, 7, 8, whatever, all the way to infinity, it's true for those values, and it's false for everything 4 and below. Since 4 is not greater than 4, that statement is false when you plug in 4. So 4, 3, 2, 1, 0, -1, -2, all the way to negative infinity. So we worked out the truth values for the statement B. Now we want the statement that has the opposite truth values. So it's true for values 4, 3, 2, 1, 0, -1, -2, -3, all the way to negative infinity, and false for anything greater than 4, 5, 6, 7, 8, all the way to positive infinity. So if you think about this, well, what do we want here? We can write this in many different ways, in fact. One way we could write it, well, we want it to be true for values 4 and below. So maybe you could write X is less than or equal to 4. And be careful here. Remember, a lot of people might just see this greater than, and they say, all right, it's a negation, I'm going to change it to a less than. But that's not quite true, because you're missing the case when X equals 4. You're not flipping the truth value of that. You could imagine, I'm going to erase the correct answer and put in the incorrect answer just for a second. So imagine somebody wrote this as the negation. Well, what happens with the value 4? Well, 4 is not greater than 4, so B is false when X equals 4. But the negation of B, we want it to be true, but 4 isn't less than 4. So we didn't flip the truth value for the number 4 in here. So this isn't a correct negation. So we should write X is less than or equal to 4. And again, we can reword this in other ways. Maybe instead you want to write X is less than 5. So there's two different ways of rewording, or of wording the negation of B. So we talked about truth values of various statements and open sentences. So now we need to determine how many objects a certain sentence applies to. And this is done using this idea of quantifiers. So they're just words that tell you something about how many objects in a group a property applies to. And there's two types of quantifiers that we really care about in math. We group them into two types. One is universal, and that tells us about all objects in a category. So some examples of that are something like all cats have paws. That tells us something about cats. We're saying everything that is a cat has a paw. And in fact, that is a true statement, of course. Another example is this one down here. No cats have wings. So no cats have wings. Well, that's true as well. It tells us something about all cats. It's saying that they don't share the property that they have wings. None of them have wings. I put a little asterisk by no, because in some sense, you can always reword a sentence that has the word no in it as its quantifier to one with all. And we're going to be talking about negating quantifiers just after I tell you what quantifiers are about. So we're going to come back to this idea a little bit later. The other type of quantifiers are existential. They just talk about if a property exists for one or more objects in a category. So you see this word exist inside existential. And that's about at least one. That's probably the best way of thinking of existential quantifiers. But you'll see words like some or there is or something like that to be an existential quantifier. So an example of one is some cats are gray. And I think most of us have seen a gray cat. All we need is one gray cat for this statement to be true. Some cats are gray. Gray cats do exist. Not all cats are gray, just some. So that is another true statement. Another one, there is a cat that is named Cletus. Now you guys might not know a cat named Cletus. I do, in fact. So that is a true statement. It might be just the one cat named Cletus. I don't know. But for this statement to be true, there just needs to be one object, one cat that satisfies the property is named Cletus. So that's how quantifiers work. All right. Here are 4 quantified statements. I want you guys to determine the truth value of these. So pause the video now, have a read of them, and see if you can determine if these are true statements or false statements. So pause the video and we'll come back in a second. Okay. So, the first one, all integers have a positive square. So let's think about that. Well, you could think you could try some, and you'd be like, all right, 1 squared is 1, and 2 squared is 4. And you could think, all right, if you square a positive number, it's positive, no problem. Positive times a positive is a positive. And same, a negative times a negative is a positive as well. So something like this, negative 4 squared is positive 16. It looks like we always get positives. But remember, it only takes one, and we'll talk about this later, one counterexample to disprove an all statement. And is there a counterexample? There is indeed. Remember, the integers are all positive numbers, negative numbers, and 0. And 0 squared is indeed 0. And 0 is not positive. Since 0 isn't positive, well, that means we found, we call it a counterexample to this universal statement. So it's not true that all integers have a positive square. So this is indeed false. Okay, let's look at 2. There is a 2-digit prime number where the sum of the digits is also prime. Well, remember, prime numbers are numbers that have exactly 2 factors, 1 and itself. And we're looking for 2-digit primes. So if we think about it, 11 is a 2-digit prime. 11 is prime. The only factors of 11 are 1 and itself. And 1 plus 1 is 2. And 2 is, of course, a prime number. The factors of 2 are 2 and 1. That's it. There's exactly 2 factors. So this is indeed a true statement. We were looking for just one value to show that this existential statement was true. There's more out there. You can check something like 23 is a prime number, and also the sum of the digits, 2 plus 3 is 5. That's also a prime number. So there's more than one example. But to show that this is true, we just need to find one. And our one example is, Well, 11 does it for us. But maybe you did 23 instead. That would work as well. The third one. No squares have the same perimeter and area. Where we're not talking about, like, they have different units, of course. Perimeter is, say, units, and area is units squared. So let's, irrespective of units, let's just talk about the number. But if we think about it, this square here that has all side lengths 4, well, the perimeter of it is just the length of the outside. 4 plus 4 plus 4 plus 4 is 16. And the area is, of course, the side length squared, since it's a square. So 4 squared, which is also 16. So the perimeter of this square is 16. The area of this square is 16. So we found something that contradicts. That's a counterexample to this statement, this no statement. So therefore, this one is false. And finally, let's look at number 4. All integers are prime or even. Can we find an integer that is not prime and not even? So let's think about it. Well, if it's not even, it must be odd. So we're looking at odd numbers, and we want odd numbers that aren't prime. So the first odd number I can think of that isn't prime is 9. So 9, it's definitely not prime, since 9 is 3 times 3. One of its factors is 3. It just doesn't have 1 in itself as a factor. So it's not prime. And it's an odd number. I can write it, if you like, as 2 times 4 plus 1. Remember, all odd numbers can be written as an even number plus 1. So we found a number where it is not prime and not even. So we found another counterexample to that one. So this is, of course, false. All right, so we talked about negation, we talked about quantifiers. Now let's talk about negating quantifiers. So let's say we have the following quantified statement. All cats are gray. Obviously that's false. So imagine that you want to tell somebody that's false. Somebody says to you, all cats are gray, and you say, that's false. What sentence would you say that would be a correct sentence? So pause the video now and see if you can write down something that is true. This is definitely false. See if you can negate it, just using kind of your intuition. What would be a true statement? This is obviously false. What is the true version of this? Okay, so if all cats are gray is false, what does that mean? Well, it means that you should be able to point at a cat that isn't gray. So the negation of A is, there is a cat that is not gray. Now let's think about what we did here. Intuitively, we know this is true. But let's think about what changes. Well, we have a new quantifier. We changed our universal to an existential. So we changed this all here to a there is. And then what did we do? Well, the object stayed the same. We're still talking about cats. So cats are still cats. But let's look at that next bit. So in the original statement it was they are gray. In the new statement, it's the negation of that. It's they are not gray. So in general, there's kind of nothing special about cats or being gray. So in general, if we have something like all whatever, let's call it P, all P are Q, the negation of that, well, you change the all to a existential quantifier, so let's say some, or there is, or at least one, something like that. The object stays the same, so some P, and we're going to just negate Q. So it's going to be they are not Q. So you just, again, flip the quantifier, negate the property. So that holds for all of these. And I do want to talk about that asterisk that came up. So this isn't necessarily a negation. Well, it is kind of a negation, but the quantifier no, so if we have the statement no P R Q, we can always reword that to something with all. So that's just going to become all P are not Q. So if something, or let's say with the last example that we had, no cats have wings. So in that case, our P is cats, our Q is has wings. Well, that's the same thing as saying all cats do not have wings. So we just changed the no to an all, and we negated the quantifier. So it's not quite a negation, but it is just a logical equivalent. So you can always change this no here to an all statement. And in some sense, mathematicians like to have as few things as possible. So we like that you can write every sentence with quantifiers logically as either a some sentence or an all sentence. So knowing that, we like to just use those two things. But just note that these are literally the same statement. No P R Q is the same as all P are not Q. So that is negating universal statements. Let's look at negating existential statements. So let's say we had the statement, there is a cat with, let's say, with 3 eyes. So again, this is ridiculous. In fact, there might be, I want something to be false, and I want it to be obviously false. Maybe there's a weird genetic defect. So let's say 7 eyes. There is a cat with 7 eyes. This is an obviously false statement. There is no cat with 7 eyes. And I'm going to reword it. That is a fine way of saying it. No cats have 7 eyes. But I'm going to use the all quantifier, just so we have a method of negation that's kind of the same. So if I want to reword it with all, well, if it's false that there is a cat with 7 eyes, then the negation of that, you'd say, well, all cats do not have 7 eyes. And again, what did we do here? We took this existential quantifier, and I should write we're doing the negation here. We took the existential quantifier and we turned it into a universal. Again, the object, of course, just stayed the same. We're talking about cats. So a final few notes about negation. So first of all, and this one's kind of obvious, if you have a double negation, of course that's just like doing nothing. So if you say something like, if a number is not negative, then it is negative. So if you have a double negation, the negations cancel. The second thing I want to talk about, and I guess second and third, is the negation of these compound statements with and or. So I just want to do a quick example of these just so you see where they're coming from. You could work these out with truth tables as well to show that they're logically equivalent, but I just want to show you this intuitively so that you understand how to think about it. So imagine I had the statement, I like coffee and I like tea. So if that's my statement there, here's my A, here's my B. Well, that is only true if both I like coffee is true and I like tea is true. Remember, ands are true exactly when both parts of the and are true. So if we wanted to negate this, if we wanted to think about a situation where this would be false, well, it's false in any other situation. So either it's false when I don't like coffee or I don't like tea. So the negation of this is I don't like coffee or I don't like tea. So that's negating an and statement. Negating an or statement, well, it's the same idea. Imagine I said something along the lines of it is warm or it is raining. So imagine I said that statement. When would this be false? Well, this would be false exactly when both of these guys are false. Remember, ors are false exactly when both parts are false. So it would be false when it is not warm and it is not raining. So the negation of this is it is not warm and it is not raining. So, and again, there's nothing special about warm and raining or coffee or tea or liking or anything like that. In general, if you have an and statement and you want to negate it, negate each part and flip the combining word. Flip the and to an or. And again, if you're negating an or statement, negate both parts and flip the or to an and.